Alright, we're ready to start a new chapter. The new chapter that we're going to look at is called Applications of Derivatives. And our first section is actually going to involve tying f prime, and f double prime into graphs. And how can I take f prime and figure out the graph of f, or f prime and figure out f double prime, and how all that's related to each other. First, we want to start by just reviewing what we were working on before. If you remember, we talked about having some problems. Matter of fact, on our test today, we did some things where we had, this was the graph of f, and you were supposed to figure out what would f prime look like. And we talked about that, remember, the derivative is slope, and since this function is decreasing at the beginning, its slope is going to have to be negative until it gets to about right here. Let's say that happens to be a 1. At right there, the slope is going to end up being 0. So when I plot the derivative over here at x is 1, we know we have to equal 0. Then after 1, we have all these positive slopes. So our slope would go back to being positive. Because our original function appears to be quadratic, then we would expect that our derivative would be linear. So then we would expect the derivative to look something like that. So if the original problem was f of x, then we would expect the derivative to look like this as a line. And then we also looked at what if it was reversed, and what if I gave you what f prime looked like. So let's do the same kind of thing. And this time, let's say that this is f prime. And we'll say that's touching at -1, and then over here at 2. Okay. What would be a possible graph of f? Well, just using our algebraic skills and remembering that, well, if the derivative is quadratic in x squared, then the original had to be a cubic. Then let's keep that in mind, and let's look at what's happening here. Now this time, we have the derivative, so we know that everything from here has a derivative that's positive. That's where the derivative is positive, which means your original function had to be increasing till it got to -1. So my graph's going to be coming up till it gets to -1 something, and right now I can't find out what that is. Then the derivative turns negative from -1 to 2. Okay. So that means it's got to be decreasing. So from -1 to wherever x is 2 is, we're decreasing. And over here at x is 2, we switch and we go back to increasing, which means that, or go back to positive for our derivative, which means our function would then have to switch to being increasing. And there you can see that that looks like a cubic. Now what we're going to do is spend our time doing the same kind of idea, but using algebra. And I think some of you are going to like that better, because you're going to have some equations to work with. It actually requires less thinking. So let's say we had this, that y equals x squared plus 8x minus 2. And I want to get the graph of that, and I want to use the derivative, the first derivative for right now, to help me do that. So what I'm going to do is I'm going to start by taking the derivative, because remember, that's going to tell me my slope. And when I do, I'm going to get 2x plus 8. Then what I'm going to do is I'm going to take the derivative, I'm going to set it equal to 0. Okay, and when I do that, I'm finding my critical points. Alright, now critical points are where the derivative is 0, or the derivative is undefined. Now for right now, we're going to work on just some polynomials today, so our derivative will not be undefined, but we will get to those types of problems. So we're going to set the derivative equal to 0. When I do that, I'm going to get the x as -4. We call -4 our critical point. Okay. Now a critical point is a possible point where this could have a maximum or a minimum. It's where our slope could possibly change. And if you look back just quickly to what we were doing previously, on this, every time our slope, this was our f of x, every time our slope changed, we got a point where the derivative was equal to 0. Okay? There are places where your Derivative can equal 0, but your slope doesn't change. And again, we'll talk about those a little bit here later. So we have a critical point of -4. Now we're going to use a sign chart. Okay, we're going to use -4 on the number line. And we need to label our sign charts. That's F prime, or since we call this Y, we'll call it Y prime. That's going to be Y prime. And we're going to do like we did with the sign charts that we used in the last chapter. We're going to pick a number smaller than -4, and we're going to substitute that into our derivative. So if I take -5, put it into my derivative, 2 times -5 plus 8, I'm going to get a negative number. All right? So after we find our critical points, our next step is going to be to fill out a sign chart. Pick a number bigger than -4. So let's do 0. If I put 0 into my derivative, now remember we're using the derivative, then I'm going to get a positive number. So now that I know what's happening with my derivative, I can tell you where this thing is increasing and decreasing. Because if you remember, when we tied this in with position, velocity, acceleration, negative velocities or negative slopes told you direction also. So if this derivative is negative, then my function had to be decreasing, and when the derivative is positive, my function was increasing. So in this case, this thing would be increasing from -4 to infinity, and we use the x values for this. And then it would be decreasing from -infinity to -4. Now what I like to do, and this sometimes helps you, especially with polynomials, is I like to then kind of draw that in on my sign chart. So here's what's happening. We decrease, then we increase. So if you notice, then at -4, we hit a low point, and we call that a local extrema. If there's one of them, it would actually be extremum, which is what we would call local maxes and mins. A local maximum or a local minimum. Now remember, those are not the highest and lowest points in the entire graph. Those are just the points kind of in their neighborhood that are the highest and lowest points. So then this also has what we would call a local minimum, because it dips down and hits a valley there. So we have a local minimum at -4. And then I would go back and put -4 into the original problem and find out what my y value was. So if I did -4 squared, okay, because we had x squared plus 8x, so plus 8 times -4, and then minus 2. So that would be 16 minus 32 and minus 2, which would be -18. So now I know where my local minimum is. Last thing, I'm ready to actually get a good sketch of this. So now, and I'm not going to count off all my tick marks here, I'm just going to label this. First thing you want to do when you're graphing is graph your local extremum, okay? So go to -4, -18, we'll just put a dot there and we'll label it. -4, -18. And now we're ready to sketch our graph. So what happens here? This graph decreases first till it gets to the minimum, and then it increases. So when I sketch that, I want to sketch it in as it decreases, then it increases. And please understand that for right now, we're just working on some rough sketches, but we now know where the vertex of that parabola would be located. Okay, let's move on, try another problem, same kind of thing, a little more involved. How about y equals x cubed minus 12x minus 5? All right, so let's take the first derivative, get 3x squared minus 12, and let's set that equal to 0. Now, because this only has an x squared in it, you could solve by getting the x by itself and then taking the square root. I'm actually going to do this by factoring, because on the polynomials, a lot of times you'll see factoring. So I'm going to take out a common factor of 3. And then x squared minus 4 is the difference of squares, so that would factor to x minus 2, x plus 2. So now I pick up my critical points. Okay. So what would make each of those equal 0? Well, 3 is never going to equal 0. X minus 2 would be equal to 0 if x was 2, and x plus 2 would equal 0 if x was negative 2. So those are my critical points, and now we're going to do our sign charts. So use -2 and 2. Pick a number smaller than negative 2, like negative 3. If I put it into my derivative, and I always go back to the factored one, it's going to be easier. That's going to be positive. Remember, I'm using negative 3. Negative 3 minus 2 would be negative. And then negative 3 plus 2 would be negative. So I have positive, negative, negative. Well, that's going to end up being positive. Pick something between negative 2 and 2, like 0. You're going to have positive, negative, positive. So that ends up being negative. Something bigger than 2, like 3, and we're going to get positive, positive, positive. Okay. Now I can write down my intervals where I'm increasing and decreasing. I can use my sign chart for that. I'm increasing from negative infinity to negative 2. Where's the derivative positive? Then I put a U because that means or. The other place I could be increasing is 2 to infinity. Then I decrease when my derivative is negative. Well, that's from negative 2 to 2. Now you need to realize that that is not an ordered pair at negative 2, 2. It's from x is negative 2 to x is positive 2. Now if I go in and kind of sketch my graph, it looks like this. We go up, then we decrease, and then we increase. And notice this is supposed to look like a cubic, and it does. So I can now tell that I have a local max at negative 2 and a local min at positive 2. And then I would take those and put them back into my original equation. And if I do that, I'll find that my local max is at negative 2, 11. Putting negative 2 back into the original equation, x cubed minus 12x minus 5. Fix that. That will give me 11, and if I put positive 2 in, I get negative 21. And now I'm ready to sketch that, and again, I'm just going to do a rough sketch real quick. We have a point at negative 2, positive 11. And then we have a minimum at 2, negative 21. And our graph increases, then decreases, then increases. So it goes up to there, comes down and hits that, and comes back around. All right, let's wrap up with one last example. And this time we'll look at one that's a quartic. Y equals x to the 4th minus 18x squared plus 3. So we'll start with our derivative, y prime. 4x cubed minus 36x. Set that equal to 0. Now we're going to look to factor. We've got 4 and 36, so we can take out a common factor of 4. We've got x cubed and x, so we can take out an x. That's going to leave me x squared minus 9, which again is a difference of squares. X minus 3, x plus 3. And now we get our critical points. Okay, so what would make 4x equal 0? 0. X minus 3 would be positive 3, and x plus 3 would be negative 3. So we're going to do our sign chart using 0, negative 3, and positive 3. All right, now that we've got our critical points, we're going to fill in our sign chart. So we pick a number smaller than negative 3, let's say negative 4. Substitute it in here. We're going to get a negative, negative, negative. So that's going to be negative. Pick something between negative 3 and 0, like negative 1. We'd have a negative, negative, and a positive. So that's going to be positive. Between 0 and 3, let's say 1. If I put 1 in, I get positive, negative, positive. So that's negative. And if something bigger than 3, like 4, we're going to get a positive, positive, positive. So that'd be positive. So this graph is going to decrease, then it's going to increase, then it's going to decrease, then it's going to increase. You can see our quartic there. So our intervals of increasing would be from negative 3 to 0. And again, since there's more than one, we put a U, and 3 to infinity. Then decreasing would be negative infinity to negative 3, u, and then 0 to 3. We also have our local maxes and mins. Let's see what we have. Now, you don't have both of those all the time, but in this case, we actually have one local max and two local mins. We've got a local max right here, where we switch from positive to negative. And so we have a local max at 0, and go back to the original function, and substitute in 0, you're going to get 3. If I do my local min, that's where I'm going to change here from decreasing to increasing, and here again. So I'm going to have a local min at negative 3 and at positive 3. Now I need to get the y values for those. So if I go back to the original, and you can put this into your calculator and check it, if I put negative 3 back into the original, you should get negative 78. If I put positive 3 in, I also get negative 78. So here's my graph. All right, so let's plot our local extremum. We have a local max at 0, 3, so we'll just plot a point there. We'll call that 0, 3. We have two local mins, one at negative 3, negative 78, and then one at positive 3, negative 78. Now, following the sign chart, we should decrease, increase, decrease, increase. So it's going to decrease to there. It's going to turn and increase. It's going to decrease, and it's going to increase. And there's a sketch of your chording.